All right, so far in this chapter, we have already said that for a galvanic cell, we're going to be utilizing a spontaneous reaction to provide us electricity, or that in an electrolytical cell, we're going to be forcing a non-spontaneous reaction to occur by applying a current to it, right? So what we're saying is that there's a relationship between the spontaneity of a reaction and the cell potential. And that's what we can be looking at right now more mathematically. So right here, if you remember, we used to talk about Gibbs free energy to look at spontaneity of reactions. If a delta G or Gibbs free energy change was less than 0, that meant that we had a spontaneous process. Now here you can see that there's a relationship between that Gibbs free energy and the cell potential as given by this equation. They are actually directly proportional. However, notice that there's a negative sign. So whenever my cell potential is positive, the whole right-hand side would become negative, and therefore the Gibbs free energy would be negative. So a spontaneous process is one where the cell potential is positive and the Gibbs free energy is therefore negative. Now the equation says that the Gibbs free energy change under standard conditions would be equal to negative n, where n represents the number of moles of electrons that are transferred in the reaction. This is basically the number of electrons before you add the two half equations. So whenever you have the same number of electrons on the reduction and on the oxidation, that is the number of electrons that you would put here. In the previous problem, for example, we had 10 electrons, and so 10 would be n. F is Faraday's constant, which its value is 96,485, and it has two different sets of units. It could be coulombs per mole of electron or joules per volt mole. In this particular case, for this equation, it's in your best interest that you utilize the joules per volt mole so that the volts can cancel away with the volts from the cell potential, and you're going to end up with your Gibbs free energy in joules per mole. Now, E0, of course, is your cell potential under standard conditions, and its units are volts. Oops, okay. All right, so moving on, let's do an example. Using the following half reactions, calculate the Gibbs free energy change for the reaction below and predict whether the reaction is spontaneous or not. Okay, so notice that they're already giving us an equation in which we have copper plus going to copper solid, which matches this copper 2 going to copper solid. And then the other one is iron solid going to iron 2 plus. So it's the opposite of this reaction, right? That means that this is the reduction, and the opposite of this one will be the oxidation. All right, so the question here is what is the delta G, and predict whether the reaction is spontaneous as written or not, right? So because this guy is the oxidation, then the cell potential of that one is going to change, right? This is going to change to be positive, positive 0.44. And the cell potential of this is going to be, let's see, is going to be equal to my 0.34 plus the 0.44 volts, and so that gives me a total of 0.78. For my cell is 0.78 volts, positive. Since it is a positive value, that means that we actually have a spontaneous process for the cell potential. Now we need to continue on anyways, and we need to find the delta G. So our delta G0 is equal to negative NF cell potential, right, at standard conditions. We already have this. Now we need to think about what is N, and I am not quite done with that yet, right? I have to look at my equations. Of course, remember that this equation is going to be reversed. We have Fe going to Fe2 plus 2 electrons. And so the two equations that I'm about to highlight are the ones that you really care about, this guy and this guy. In this particular case, they both have 2 electrons, so I'm actually done. I can go ahead and say that N is going to be equal to 2 because I have 2 electrons here, and 2 electrons here, and that is my number of electrons. If instead I had different numbers of electrons on both of these, I would have to multiply them by coefficients as needed to get to the same number of electrons. That same number of electrons, that would be your n. In this case, n is equal to 2. All right, so from there I can go ahead and plug everything in. So I can say my delta G at standard condition is going to be equal to negative n, which is equal to 2, F, which is Faraday's constant, which is 96,400, oops, that's 485. And the units of that is joules per volt mole. And that's multiplied by my cell potential, which we said was 0.78 volts. When you put all of this in the calculator, you should hopefully get the same answer that I did, which is negative 1.5 times 10 to the 5 joules per mole. And since we have a negative Gibbs free energy, that also tells us that we do have a spontaneous reaction, right? So in this case, we have a spontaneous reaction because our cell potential is positive and our Gibbs free energy is negative. And notice that in this case, we did have to use the top equation because there was a chance that this was not a spontaneous reaction. So if there's a chance, you do have to follow the equation that you were given to see which one is the reduction, which one is the oxidation, which one needs to flip. All right, let's move on. Now, this is the equation that we just talked about that relates the cell potential to Gibbs free energy, right? In the past, we had already seen an equation, I think this was in the previous chapter, that related the Gibbs free energy to the value of the equilibrium constant K, right? We knew that delta G0 was equal to negative RT ln K. Now, if I go ahead and put these equations equal to each other, since they're both equal to delta G0, I would get negative NFE is equal to negative RT ln K. And if I rearrange that equation to solve for the E, I would end up with this equation. And this is an equation that is new and that you need to know. And basically, this equation allows you to relate the cell potential to the equilibrium constant K. Okay, so that's an important equation. All right, everything else in that equation, you know what it is. R is your gas constant, T is the temperature in degrees Kelvin, N is the number of electrons that are being transferred, just as in the previous problem. F is Faraday's constant, and again, K is your equilibrium constant for whatever equilibrium process you're talking about. All right, now, so far we have been talking about standard conditions. What we're going to be looking at here is what happens if we have concentrations other than 1 molar. What effect is that going to have on our cell potential? And that's important because it allows us to see, how can we change the voltage that this cell is going to provide us by changing the concentrations? Or what happens when the reactants get used up and we run out of potential, right? Our battery basically runs dead. All right, so how does the cell potential vary with concentration? Standard conditions include solutions with a concentration of 1 molar. So just to remind you, this is what standard conditions is. When the concentration is not 1 molar, then we're going to use 2 different methods. The first method is to utilize Le Chatelier's principle to help us predict the effect. And the second method, which I don't have written here, is the Nernst equation, which is just a few slides below. Nernst equation. So let's go ahead and write it down. This is method number 1. Method number 2 is the Nernst equation. Okay, let's go ahead and get to it. So in this problem, we're going to use Le Chatelier's principle to predict what happens if the concentrations are not 1 molar. So to begin with, we're going to look at the equation. We have aluminum and manganese ions reacting to form aluminum ions and manganese metal. Predict whether the cell potential is going to be larger or smaller than the standard cell potential for the following 2 cases. The first case is where I have aluminum ions having a higher concentration than the 1 molar. So this is all that I care for, the fact that aluminum ions have a higher concentration. This is my aluminum ions. If their concentration is higher, you can think about it as basically we just added more aluminum. And if we added more aluminum, that's going to have a shift in the equilibrium toward the left-hand side of the equation. And if I have a shift toward the left, that means that my cell potential is going to be lower than it would have been if the concentration had been 1 molar. So because I have a shift to the left, I'm going to have a cell potential that is actually smaller than the standard cell potential. Now let's look at part B. In part B, what we have is, let's see, we have a higher concentration of the manganese ions, 3 molar. So the manganese is higher, which means that I just added a bunch of manganese ions. That's going to cause a shift in my equilibrium to the other side, which means that I'm going more to the right. My reaction is happening more and more. That means that my cell potential is actually going to increase. So shift to the right is going to cause the cell potential under non-standard conditions to be greater than the cell potential at standard conditions. All right, I hope that that makes sense to you guys. Now, the other method that I told you that you can use whenever you have different concentrations is to use Nernst equation. So Nernst equation allows you to calculate the cell potential under non-standard conditions, and it also allows you to see what is the effect of component concentrations on the cell potential. So here's the equation. It says that the cell potential under non-standard conditions is going to be equal to the cell potential at standard conditions minus this whole term. In this term, R is your gas constant, which is 8.314 joules per mole Kelvin. T is your temperature in degrees Kelvin. N is the number of electrons that are being transferred. Again, that's the number of electrons that is equal between your reduction and your oxidation. F is Faraday's constant, and that's 96,485 joules per mole per volt mole. And this is what you're going to be using. And then L and Q, where Q is your, I didn't write it down, but Q is your reaction quotient. And the reaction quotient, remember that you calculate it in the same way that you calculate your equilibrium constant, meaning the product concentrations over the reactant concentrations, each of them raised to their individual exponent, right? And of course, this basically enables you to have different concentrations other than 1 molar. And then the T here allows you to have temperatures other than 298 Kelvin. One thing that I want to go ahead and mention really quickly is that you do want to be careful with the units. Notice that Faraday's constant is in joules, R is in joules, that's good. That means that your cell potential, actually the joules are going to end up canceling away, so that's okay. So I think you should be okay with the units, never mind, you should be okay because this guy is in volts and this will end up being in volts as well. You're okay with the units. Now, there's another version of this equation. If you are at 25 degrees Celsius, you can actually plug in the values for R, for T, and for F, and those three together end up being 0.0591. And so in your equation, now you have less variables. So again, if you are at 25 degrees Celsius, then this equation is valid because it has already replaced R, T, and F with this number. But notice also that what they do is also they change the ln natural log to a log, log base 10. So be careful if you use this equation, make sure that you use the proper logarithm. All right, let's do an example. So calculate the cell potential for the galvanic cell, which is based on the following two half reactions. When the concentrations of silver ion, hydrogen peroxide, and hydrogen ion are as such. Notice immediately that we are given concentrations that are other than 1 molar, which means that we are under non-standard conditions. All right, so we need to think about this. We do have a galvanic cell, which means that we have to figure out which of these two equations is going to be the reduction and which one is going to be the oxidation, because right now they are both written as reductions with the electrons on the left-hand side of the equation. And so we're going to look at the values of these two. Whichever one is more positive, which is this guy, will be the reduction, right? So this is going to be our reduction. I'm going to go ahead and relabel. And that means that this is going to be our oxidation, but that one is going to change its sign to become negative. All right, and so I'm going to go ahead and highlight this guy and this. But for this guy, I'm going to have to change the order of it. This is going to be Ag going into Ag plus an electron, and this is its cell potential because I already changed the sign. Awesome. All right, so we need to calculate the cell potential, right? But we are under non-standard conditions. So we know that we're going to have to use Nernst equation. And I'm just going to go ahead and write it here. I'm going to say E is going to be equal to our cell potential at standard conditions minus RT over NF ln Q. Okay, the Q is going to account for the different concentrations. And then to be able to solve for this, we actually do need the cell potential at standard conditions. How do we calculate this one? Well, we already know that we can calculate it by adding these two values. So our cell potential at standard conditions is equal to our reduction potential, which is 1.78 volts, plus the oxidation potential, which is negative 0.80 volts. And that is equal to, oops, that did not look very good. Oh, come on. E0 is equal to, let's see, where do I have my value? 0.98 volts. All right, so we have the E naught. We're done with that one. In addition here, we were not given the temperature, so we are okay to assume 298 Kelvin or 25 degrees Celsius. The value of R, we know it. We need N. N is the number of electrons that are being transferred. But notice that here I have one electron and here we have two electrons. In order for us to be able to combine the two equations, we need to have the same number of electrons. In this particular case, the smallest multiple that is common is going to be 2. So I would be taking this equation right here and basically multiplying by 2. And that means that I'm going to end up with 2 electrons. So N is going to be equal to 2. Now I'm going to go ahead and write that here. Again, N is the number of electrons that is being transferred overall between the two equations. F, we know it, and then the last thing that we need is Q, our reaction quotient. So let's work on the reaction quotient right now. To be able to figure out the reaction quotient, we actually need the overall balanced equation. So that's what we're going to work on now. The overall balanced equation is done by taking these two equations and adding them together. And if you don't mind, I'm not going to rewrite everything. I'm just going to actually do it right now kind of in our heads. We know that the electrons are going to cancel away. Everything else is going to come down because I don't see anything else that would cancel. So I'm going to start with my two AGs. These are these guys. The other stuff that I have on the left-hand side is this. I'm going to have hydrogen peroxide, H2O2. I'm going to have the two hydrogen ions. Oops, I forgot the plus sign. Plus 2 hydrogen ions. The electrons cancel away. There's nothing else on the left-hand side. Now, on the right-hand side, we're going to have our 2 silver ions, as well as the 2 waters that are left. All right, now this is our balanced equation. From here, remember that the next thing that we're going to have to find is going to be our reaction quotient. And to be able to properly do the reaction quotient, we'll need to know what the phases of our reactants and products are so that we know what to omit. Remember that we're going to be omitting solids as well as pure liquids. So to begin with, here we have 2 silver. This is silver metal. Silver metal is a solid. Hydrogen peroxide is actually going to be in solution, so this is going to be AQ. Any ion that you have as a soluble ion is going to be AQ. So this same thing here. Oops. That says AQ, okay? And then the last one, our water, is going to be a pure liquid. Let's see if it'll let me actually write. Here we go, pure liquid. Wonderful. So from here, we're going to go ahead and write our reaction quotient. Remember that the reaction quotient is found exactly as equilibrium constant expression would be, which is products over reactants, each of them raised to their own coefficient. So looking at my products, the only thing that I actually have to include is my silver ions. So I'm going to put Ag plus, and this is going to be squared because of, oops, because of its coefficient. Come on, let me write, computer. 2, thank you. Divided by my reactants. I will be omitting the solid silver, and the only things that I have to include are therefore the hydrogen peroxide, H2O2, and my hydrogen ions. The hydrogen ions will have to be raised to the power of 2 because of the coefficient of 2. And I forgot to mention here, but remember that we always omit pure liquids as well, just as well as solids. All right, so from here, we're going to go ahead and put the concentrations. So let me back up here where we can see those concentrations. Notice that for silver ions, we have a concentration of 1, so 1.0 molar, and that's going to be squared, divided by the concentration of hydrogen peroxide, which is 2 molar, to the power of 1, and then times the concentration of H plus, which is 2.0 molar, but this one is raised to the power of 2. When you put this into the calculator, the answer will be 0.125. Let's see if I can write that a little better. Nope, it's not gonna let me. All right, let me move down here and see if it'll let me now. 0.125. Okay, and that is a dimensionless quantity. From here, the last thing that we have to do is to plug everything back into the Nernst equation. Remember that our Nernst equation, we wrote it up here, which says that the cell potential will be equal to the cell potential under standard conditions, which we calculated here. That was a 0.98 volts. And that's going to be minus R, where R is our gas constant, and that's 8.314 joules per mole Kelvin. And I apologize for my writing, but it's really not letting me. That's supposed to be a J. Come on. I wrote, yeah, okay. Times the temperature, which is 298 Kelvin. Notice that in this problem, we actually were not given a temperature. So whenever you are not given a temperature, it is okay for you to assume standard temperature, which is 298 Kelvin or 25 degrees Celsius. This is divided by n, where we said that n was 2, or the number of electrons that is being transferred in between the reduction and oxidation reactions. And then finally, Faraday's constant, which is 96,485, and that's joules per mole volt. All right. The joules per mole are going to cancel. The Kelvin degrees will cancel away. The only unit that we have left is going to be our volts, which is good because that's what we need. And then, of course, don't forget the natural log of 0.125, which is our reaction quotient. All right. When you plug this into the calculator, you should get your answer as 1.01 volts. And we are done with that calculation. All right, so just to recap, what we ended up doing in this problem is that we knew that since we were under non-standard conditions, we needed to utilize the Nernst equation. To be able to solve this, of course, we need the cell potential under standard conditions, which is found by adding the oxidation and the reduction potentials. We then went to find the number of electrons that were being transferred, and to do that, we basically have the two balanced equations for reduction and oxidation, and we modify them to have the same number of electrons. And in this case, that was 2 electrons here, 2 electrons here, and that's what N is. The last thing that we needed to do was to find the reaction quotient. To find the reaction quotient, we actually need the fully balanced equation. So we actually took these two half equations, added them together to get this balanced, fully balanced redox equation. And from there, we used the phase symbols to determine which of these substances actually needed to be part of the equilibrium and therefore part of the reaction quotient. The last thing that we did was to plug all the values into our cell potential equation, into the Nernst equation to find the potential. That's that. So, whenever you start with a galvanic cell, I guess, you start with a specific concentration of your reactants and products, right? Over time, those reactants are going to react, and eventually their concentration is going to be very low, and eventually is going to be zero. In fact, if you look at the equation, over time, this is going to change until you reach equilibrium, at which point we're going to have ln K here. And if you remember, the equation for E0 was RT over NF times ln K. And so eventually you're going to have E0 minus E0. So eventually you're going to have cell potential of 0. And therefore you're going to have a dead battery. No more potential to drive your electronic device. So that's something to keep in mind.